At the very bottom of our world lies a landscape defined by absolute extremes. Pounding winds sweep across this cracked, barren expanse of ice and jagged stone, isolating it entirely from the rest of the planet. This 3D diagram illustrates the staggering scale of the ice sheet covering the landmass. In some places, the ice reaches 5 kilometers thick, dwarfing any structure humans have ever built. Locked inside this frozen mass is nearly 60. If we plunge beneath the surface, we find a perfectly preserved record of Earth's ancient history, waiting to be read. Because the snow in Antarctica rarely melts, each fallen layer creates a permanent physical timeline. Drilling kilometers deep into the ice sheet, researchers extract long, solid cylinders known as ice cores. Within these transparent cylinders are tiny pockets of ancient air. These bubbles are perfectly preserved, undisturbed samples of Earth's atmosphere, dating back hundreds of thousands of years. Measuring these gases uncovered a shift in the planet's pulse. While Earth once cycled between warm and cold every 40,000 years, data shows that 1 million years ago, those cycles stretched into massive 100,000-year intervals seen today. By analyzing the chemical composition of these ancient gases, scientists established the baseline of our planet's historical climate, allowing them to build highly accurate predictive models for our immediate future. If we drill entirely through the ice sheet, we break into an environment completely cut off from the surface. Down here, an interconnected network of over 400 subglacial lakes and rivers flows across the bedrock. When researchers lowered cameras into these pitch-black subglacial channels, they documented thousands of translucent, shrimp-like amphipods. These complex organisms are actively swimming and thriving in water sealed away from sunlight for millions of years. Further along the ice shelves, the Taylor Glacier presents a highly visible anomaly, a crimson waterfall known as blood falls. This water seeps from a hypersaline subglacial reservoir. Saturated with dissolved iron, it oxidizes and rusts immediately upon contact with the surface air. Inside this toxic, completely oxygen-free reservoir, 17 different species of bacteria survive. They sustain themselves entirely by feeding on the dissolved iron and sulfates within the dark water. These microscopic extremophiles demonstrate how biology adapts to total darkness and intense pressure. For astrobiologists, this isolated ecosystem serves as a working blueprint for how life might survive in the subterranean oceans of frozen moons like Europa. This radar scan peels back flat surface ice to reveal the hidden Gambardseff mountain range, spanning over 1,200 kilometers. These peaks remain sharp and jagged, as if recently thrust upward, showing none of the gradual erosion usually seen in dormant tectonic plates. Deeper investigation into the coastal bedrock and marine sediment has yielded physical material from the Cretaceous period. Expeditions have pulled up fossilized roots, ancient microscopic pollen, and perfectly preserved 90-million-year-old seeds. Paleontologists working in the exposed rocky corridors of the transantarctic mountains have unearthed massive dinosaur bones and marine reptiles embedded directly in the stone. These discoveries confirm that during the high carbon dioxide levels of the Cretaceous period, Antarctica was a warm, temperate rainforest. It operated as a thriving ecological highway for giant fauna long before continental drift moved it to the planet's freezing southern pole. Returning to the surface, the physical mechanics of the ice sheet perform another function. As massive glaciers slowly drift and collide with mountain ranges, they act like a conveyor belt, pushing and concentrating fallen cosmic debris against the rock. This glacial movement turns the stark blue ice fields into the Earth's most productive meteorite hunting ground. The continent's natural deep freeze preserves these dark space rocks in pristine condition against the highly visible white and blue background. In 1984, researchers recovered this stone, designated ALH 84001. Chemical analysis of trapped gases matched data from planetary probes, confirming it was blasted off Mars by an asteroid impact 4 billion years ago. Inside this Martian meteorite, scientists identified specific minerals that only form in the presence of liquid water. This physical specimen provided concrete proof that water once flowed abundantly across the ancient Martian surface. Antarctica functions as the primary regulator of Earth's modern climate system. This map displays the global ocean conveyor belt known as thermohaline circulation. Freezing, highly saline water from the Antarctic coast becomes incredibly dense and sinks to the ocean floor. This sinking action creates a powerful current that radiates outward, driving global ocean circulation and regulating weather patterns across every other continent. Today, as global temperatures rise, this boundary between the ocean and the ice is absorbing massive thermal stress. The structural integrity of these coastal ice shelves is rapidly degrading. If the Antarctic ice sheet destabilizes and collapses into the ocean, it holds enough freshwater to raise global sea levels by 200 feet. A melt of that magnitude would permanently submerge coastal cities and alter the geographic borders of the planet. The records preserved in the ice provide the high-resolution data needed to model how the planet responds to rising carbon and thermal stress. Understanding the history locked in this fault is the tool we need to prepare for our climate future.